Hello and good afternoon friends, welcome to the CEC-UGC live lecture. Dear friends, in our previous session we discussed on solutions in detail. Dear friends, taking the lecture forward, today also we would be grabbing maximum knowledge on solutions, and for this discussion we have once again with us in our studios Dr. Amit Kumar. Dr. Amit Kumar is Assistant Professor in Department of Chemistry, Dayal Singh College, University of Delhi. So let's welcome our guest Dr. Amit Kumar and let's try to get deep insight into the topic solutions. Hello sir, welcome to today's lecture.
Thank you very much, Kitika. First of all, I wish very good afternoon to all the dear viewers. Dear viewers, as you have been apprised of that we have been having details about solutions chapter in the phase equilibria topic. So now we'll continue with the solutions chapter with the discussion of the Rolle's law, its implications on a binary solution having a non-volatile solute dissolved in a volatile liquid solvent, as well as when we go to mix two volatile liquids to form a binary solution. We would like to see the implication of the Rolle's law onto this phase equilibria, that is the equilibria between a condensed phase, that is liquid system, and the vapor phase with which it is in equilibrium. This is all we have to see in today's lecture. So for that we shall start in this way, that let us first of all consider what is vapor pressure of a solution. Vapor pressure is just nothing but the pressure exerted by the vapors in equilibrium, that are in equilibrium with a solid phase or a liquid phase of a substance. Now if the substance is in the liquid phase, so the pressure exerted by the vapors arising from the liquid with which it is in equilibrium is called its vapor pressure. Now let us see what happens when a non-volatile solute is dissolved in a volatile liquid solvent. We have been having the definition of a volatile substance earlier on in our previous lecture in solution chapter, and we know that a solution that a substance which is capable of undergoing evaporation and leading to the formation of vapors which may exert pressure. This pressure is actually the vapor pressure of that liquid substance. Now it is important to note that if suppose a non-volatile solute is dissolved in a volatile liquid solvent, so since the solute is non-volatile, it will not undergo evaporation, or it will therefore will not exert any vapor pressure. So what happens, it has been observed that when a non-volatile solute is dissolved in a volatile liquid solvent, the vapor pressure of the resultant system is found to be less than the vapor pressure of the pure liquid at the same temperature. So having said this, so it becomes important to understand, is there any quantitative relationship between the vapor pressure of a solution and its composition? The answer to this question comes right from the discussion of the Rolle's law. Francois Rolle, a French chemist, has exactly managed to discuss or to understand the relationship between the vapor pressure of the solution with its composition. So let us see what he tried to do. You see, if we say that we have only liquid phase, pure volatile liquid solvent, and if we designate symbol A, that may be associated with our solvent, and symbol B if we designate with our solute. And if the solute is non-volatile and solvent is the only volatile substance if we have, then what it does mean is that at a fixed temperature, let us say T, if the amount fraction of the system is such that XA, amount fraction of component A, that is volatile solvent, that is equal to 1, in that situation it means we have only pure volatile solvent, or in other words the component A in the mixture. And in that situation the vapor pressure of the system would be the vapor pressure of pure liquid solvent, because you have in the system only pure liquid solvent. So, therefore, PA naught, which is just nothing but the vapor pressure of pure liquid A, naught is been placed over PA. PA means the vapor pressure of component A. When a naught is also introduced as superscript, it does mean that we are talking about pure component. So, PA naught is the vapor pressure of pure component A, and this is the point A on the pressure versus composition diagram which designate this vapor pressure of pure component A, that is PA naught. Now, if we have in our system, if we say that there is only component B or the solute we have, and solute is not solute does not undergo vaporization. So, therefore, when XB is equal to 1, or in other words, if we have only solute in the system, in that situation we have the vapor pressure of the system as 0, because there is no any chemical species which is volatile, which can exert some which can lead to formation of vapors, or in other words, which can exert some vapor pressure. If it is so, then in that situation vapor pressure of the system in that situation would be equal to 0. So, it means we have two extreme situations. If we have only pure component A in the pure state, in that situation we have vapor pressure of the system that is equal to the pressure exerted by vapors of the pure component A, that is equal to PA naught. And when we have pure solute in the system, and since the solute is non-volatile, so therefore pressure exerted by the system in that situation would be equal to 0, vapor pressure I am talking about. So, it means that if the system, these are two extreme situations, one when you have only pure liquid solvent, the other when you have only pure solute in the system. It could be a possibility that we may have a combination of both solute and the solvent, such that we have a mixture of the two components. In that situation, we have the composition of the system in a way that XA would vary in between 0 and 1, and XB would also vary between 0 and 1. In that situation, the vapor pressure would then be would be lying in between vapor pressure of pure component A, that is PA naught, and 0. This should be the range of pressure values within which, depending upon the composition, the vapor pressure of the resultant solution as a result of formation of solution in different proportion, it would lead to the value of vapor pressure, which would lie somewhere in between 0 and vapor pressure of pure component A. So, if we look at it, if we say that let us connect the 2 points, that is point A, which represent vapor pressure of pure component A at XA equal to 1, with that of point B on vapor pressure versus composition curve, where the pointer is pointing out to you, and this point B represent amount fraction component B equal to 0 and amount fraction component amount fraction component B equal to 1 and amount fraction component A equal to 0. So, in that situation vapor pressure would be 0. So, now if we connect, it means if we connect these 2 points, Raoult says, Francois-Raoult says the vapor pressure of the solution which results as a result of addition of non-volatile solute to a volatile liquid solvent, the vapor pressure should decrease in proportion to the composition of the solution phase, or in other words would decrease in proportion to the increase in amount fraction of solute, and or in other words would be directly proportional to composition of the solution. So, since this is a straight line, we can prove this point also mathematically. Let us have a look at it. Since this is a straight line, and we all know this line segment AB, which is a straight line, has a equation of a straight line that is equal to y equal to mx plus c. But on y axis we have pressure, and on x axis we have denoted composition, that is amount fraction of component A or B, either of the two we may take. So, on the y axis, since pressure is there, so in the equation y equal to mx plus c, we may take P instead of y variable. Similarly, P therefore equal to mx plus c, and x is the x is nothing but the variable on the x axis, which in this case we have chosen x be the amount fraction of component B. So, the linear equation of line segment AB is become P equal to mxb plus C. Now, we can consider two extreme situations. Let us say we have only pure solute in the solution in the system. So, xb in that situation would be equal to 0. If in that situation we can say we have only pure solvent, not the solute. Let this be correct, let this correction be made over here. So, xb when is equal to 0, it means we have only pure liquid solvent. Then in that situation the vapor pressure of the system would be equal to vapor pressure of pure component A. So, it means P in that situation would be equal to Pa naught and xb equal to 0. With these 2 points we can substitute in this equation P equal to mxb plus C. So, P is equal to Pa naught and xb equal to 0. So, we have C equal to Pa naught. So, in this by looking at this one extreme situation, we have been able to evaluate the value of this constant C. Now, coming over to value of the slope m of this straight line, we may evaluate, we may choose in a way that we may choose another extreme position where xb is equal to 1. When we say xb is equal to 1, it means only solute is there in the system, and in that situation it would not exert any vapor pressure because solute is non-volatile in a way. So, therefore, P would be equal to 0. So, we can put these two values in again in the equation P equal to mxb plus C, you can see, and then you will get instead of P you can write you can substitute 0, and for xb you can substitute 1. So, 0 equal to m plus C. So, therefore, m equal to minus C, and C we have already evaluated as Pa naught. So, we can substitute. So, it means m equal to minus Pa naught. So, we have evaluated C as Pa naught plus Pa naught, and therefore, m we have evaluated as minus Pa naught. Now, making use of these two values in the equation, again P equal to mx2 plus C, what we get is instead of m we can put Pa naught, and instead of C we can put plus Pa naught. So, what we get is P equal to minus Pa naught xb plus Pa naught. So, we can take Pa naught common. So, it gives rise to P equal to 1 minus xb into Pa naught. So, therefore, 1 minus xb is equal to xa. So, therefore, P equal to xa Pa naught. So, this is what is called as the Rolle's law equation, which says when a non-volatile solute, that is component B, is introduced in a volatile liquid solvent and is dissolved in it, then the vapor pressure of the resultant solution is equal to amount fraction of component A times the vapor pressure of pure component A. So, it is the product of amount fraction of component A and vapor pressure of pure component A, which is equal to vapor pressure of the resultant solution. So, this is so when you have a volatile liquid solvent and in it when you dissolve a non-volatile solute. So, it means, so therefore, this is a equation which we have obtained here is an equation of a straight line which is obtained when we join 2 points. One point on the pressure versus composition axis where amount fraction component A equal to 1 and P equal to Pa naught, and the other point when amount fraction component B equal to 1 and P equal to 0. These are two extreme points. When we join them, a straight line is obtained. This straight line gives the value of the vapor pressure of the solution, which is formed by a dissolution of a non-volatile solute in a volatile liquid solvent in different proportion. This gives the vapor pressure at different values of amount fractions of component A or component B in the system. So, it means Rolle's laws give a quantitative relationship between the vapor pressure of the solution and the amount fraction of various components in the solution, or in other words the composition of the solution. Having said this, it is now a possibility that since Francois-Raoult was working on liquid mixtures which were closely related in nature like benzene and toluene, for this is just one example. So, these two are closely related in a way that the nature of both these liquids, both benzene and toluene, is very similar, because there is a structural similarity between the two, with the only difference is that in toluene there is one CH3 group is been there in place of one H hydrogen atom in the benzene ring. So, therefore, for such kind of liquid pairs, Francois-Roult could have this relationship going very well, but for others this Rolt's law could not be followed. So, when a Rolt law is being followed by all the constituents or all the components of a solution over the entire range of composition, then we would say the solution to be an ideal in nature. That means for such a solution, the vapor pressure of the solution can easily be predicted by the Rolt's law equation easily, and it all lies on the straight line being joined by the two extreme points of the vapor pressure versus composition of the two pure components. Now, having said this, we may consider now a solution which is being formed by a combination of two liquids, rather than dissolving a non-volatile solute in a volatile liquid solvent. We may consider two liquid pairs, both of which are two liquids which go to make a pair, and both of which are volatile in nature, and they go to mix. When they are mixed, they go to form a solution, and the vapor pressure of such a solution will be equal to the sum of vapor pressures of both the liquids, or in other words the partial vapor pressure of both the liquids, because when both the liquids are volatile, they will exert their own vapor pressures. So, therefore, the total vapor pressure in that situation would be the sum of vapor pressures of partial vapor pressures of both the liquids. Now, having said this, in that situation, according to the Rolt's law, the partial vapor pressure of each constituent over the solution can be obtained by the relation, that is the product of amount fraction of that particular component times the vapor pressure of that pure component. For example, the partial vapor pressure of component A is equal to the product of amount fraction of component A in solution multiplied with the vapor pressure of pure component A. And similarly, partial vapor pressure of component B can also be obtained in this manner using the Rolt's law as the product of amount fraction of component B times the partial times the vapor pressure of pure component B. So, therefore, with the only difference in this situation is that instead of total vapor pressure being related to vapor pressure of pure component A, that is volatile solvent, multiplied with its amount fraction, here the P it is now related to PA rather than P total, because both the liquids are now volatile in nature, and they will exert their own vapor pressure, and these vapor pressure values are just nothing but the partial vapor pressure values of both these components. Right, having said this, now it is time to understand certain formulations on the basis of which we may discuss very many physical observations. For example, the total vapor pressure is equal to the sum of partial vapor pressures of both the liquids, that is P, which is a symbol which is used for total vapor pressure. This is equal to PA, the partial vapor pressure of component A, plus PB, that is the partial vapor pressure of component B. Now, having said this, we know that from Rolt's law we can make use of the Rolt's law and we can substitute for PA and PB, and PA is equal to XA PA naught and PB equal to XB PB naught. So, we can substitute the two values over here, and what we get is P equal to XA PA naught plus XB PB naught. Now, what we can do is, since both this X is a symbol which has been used for amount fraction, of this component A and component B in the liquid phase. So therefore, both the components are present in one single phase. So it means xb equal to 1 minus xa, because their values varies between 0 and 1. These are extreme values. So since their values vary between 0 and 1, so these are complementary in nature. So therefore, we can substitute for xb as 1 minus xa. So therefore, now when we do so, and when we open this equation up, so it gives us xa pa naught plus pb naught minus xa pa naught, and when we take pa naught common from the two terms which have xa, when we take xa common from the two terms, what we get is, by rearranging the equation, we get p equal to pb naught plus pa naught minus pb not xa. What it does mean? Now this thing we should have a look at it. This is the total vapor pressure P, which is equal to Pb naught, vapor pressure of pure component B, plus the difference between vapor pressure of pure component A and B, that is Pa naught minus Pb naught, that is multiplied with amount fraction of component A. So this is the equation which says that the vapor pressure of total vapor pressure of the solution, which is being formed by mixing two volatile liquids, the total vapor pressure of the solution lies between vapor pressure of pure component A and vapor pressure of pure component B, which you can plot and you can see for yourself this equation results. And you will see by way of a diagram that this would be like the curve for vapor pressure of the solution, which is formed by dissolution of two components, two liquids, two volatile liquids, that is B and A, and therefore you can see if B is less volatile, means its vapor pressure of pure component B at a particular temperature is less than that of pure component A. So therefore, since B is here less volatile, so you can see easily the vapor pressure of the solution anywhere as per the composition of solution lies in between the vapor pressure of pure component B and pure component A. Alright, having said this, let us once again revisit this equation over here. Now we know there is Dalton law of partial pressure. According to it, if we have a gaseous mixture, and if we have a gaseous mixture, since gases are miscible in all proportions, so in that situation in the system, we will have a solution being formed, since gases are miscible in all proportion. So therefore, we have just one solution. So therefore, we would represent the amount fraction of various components or various gases being present in the system by a symbol Y. Amount fraction in vapor phase would in this whole chapter would be given by symbol Y. When we put subscript A to Y, it means we are designating, we are giving a symbol for amount fraction of component A in vapor phase. When we write Y subscript capital B, it means we are giving symbol for vapor for amount fraction of component B in the vapor phase, and so on and so forth. So if we have a gaseous mixture, for gaseous mixture we have Dalton's law of partial pressure, and according to the Dalton's law of partial pressure, the partial pressure of a gas is equal to the amount fraction of that particular gas in the gaseous system multiplied by the total pressure of the system. So therefore, if we rearrange this equation, then what we get is that amount fraction of that gas equal to partial vapor pressure of that gas divided by total vapor pressure in the solution. That is what we get as the formula for amount fraction of any particular component in the gas phase when it is present in a gaseous mixture. So according to Dalton's law of partial pressure, we have Ya, which is equal to Pa that is partial vapor pressure of component A divided by P, that is total pressure of the solution. Alright. Now this would be equal to, as we have already discussed according to the Rolle's law, we have partial vapor pressure of any component equal to XA PA naught. PA naught is vapor pressure of pure component A. So XA PA naught we can write in the numerator. Since the total vapor pressure of a solution is equal to PB naught plus PA naught minus PB naught XA, so here we can substitute with this expression in the denominator for P what we get as YA in terms of XA and PA naught. These are very important relationships one must understand. That is, PA naught is the vapor pressure of pure component A, PB naught is vapor pressure of pure component B, and XA is amount fraction of component A in liquid phase. So it means if we have composition in liquid phase and vapor pressure of pure component A and B, then we can easily obtain amount fraction of a particular component in the vapor phase. It means if we have a liquid phase is in equilibrium with vapor phase, then if we know the liquid phase composition and vapor pressure of pure components, we can easily obtain composition in vapor phase, or vice versa also. That is, if we have a composition in vapor phase and also the vapor pressure of pure components A and B, in that situation we can easily obtain composition in liquid phase. So like you can have a look at it, we can rearrange this equation which gives y equal to XA PA naught divided by PB naught plus PA naught minus PB naught into XA. When we rearrange it, that is all the denominator we can multiply with YA and we can collect all the XA terms together from right and left hand side at one side, and we will get what is the rearranged value of the multiple of XA as this, and what we get is XA equal to YA PB naught divided by PA naught plus PB naught minus PA naught times YA. So you can see there is a similarity between the two relationship, one which relate composition in vapor phase YA with composition in liquid phase. In this, PA naught XA is been there in the numerator. However, when XA is been obtained with respect to composition in vapor phase YA, that is YA is been there instead of XA, but instead of PA naught we have PB naught, and all the terms which have PA naught or PB naught, now in this XA relationship you can notice that they have been replaced, A with replaced B and B with replaced with A. So therefore we get a relationship XA equal to YA PB naught divided by PA naught plus PB naught minus PA naught into YA. What I mean to say is that these two relationships, one can set up a easy mnemonic. One need not remember these formulas. What one needs to do is that one needs to know that vapor pressure, total vapor pressure of solution is sum of partial vapor pressures of component A and B, that is P equal to PA plus PB. Then write Rolle's law equation for PA and PB, substitute for them, get PA naught XA PA naught plus XB PB naught, and then put XB equal to 1 minus XA, and can easily obtain P total equal to PB naught plus PA naught minus PB naught into XA. This is equal to P total, and YA equal to PA divided by P total, and PA equal to XA PA naught divided by P total. Expression value you can use PB naught plus PA naught minus PB naught in bracket multiplied with XA. That is all expression on right side become equal to YA, the expression for the amount fraction in vapor phase. Now if you want to rearrange this equation and want to obtain XA in terms of YA, you can do easily. Simple mnemonic is that wherever there is XA, put YA, and wherever Y is YA, put XA, and instead of writing, if there is PA naught, you can use PV naught. If there is PV naught, you can use PA naught. So, alternatively you can look for this change in formula. That means, if you have formula for YA equal in terms of XA, then you can rearrange you can interchange the subscript values or the P values. What you get is, you can easily, in a mnemonic way, you can remember what way to go about XA, and you can easily write that XA. So, these relationships are very important in a way that when you are given vapor pressure of pure component A and B, and you are also given composition in vapor phase, you can obtain composition in liquid phase, or vice versa. So, we shall look at more implications of these formulas and phase diagram discussion based on these formulas in our next module. Thank you. Alright, in the previous module we had seen, we had looked at relationship between total vapor pressure and composition in the liquid phase, and we have also obtained relationship between composition in liquid phase and vapor phase, and vice versa, if the vapor pressure of pure components A and B were given to us. Now, it is time for us to explore upon, can we have or can we obtain vapor pressure, total vapor pressure of solution, a relationship, can we obtain a relationship between total vapor pressure of solution and composition in vapor phase? That is a question. So, in order to do that, let us have a look at it. Let us have a close look what formulas we had derived till the point of time. You can see this is the first formula which we had already derived, that is, which relates the total vapor pressure with composition in liquid phase, that is XA. That is P equal to PV naught plus PA naught minus PB naught into XA. Now, we have just derived the relationship between XA and YA also, this relationship I am talking about. So, this is the relationship which we can choose to write over here, that is XA equal to YA PB naught divided by PA naught plus PB naught minus PA naught YA. We can substitute the value of XA in the first equation instead of XA to get this third equation, that is P equal to, that this P is total vapor pressure of solution equal to PV naught, vapor pressure of pure component B plus PA naught minus PB naught, that is difference between vapor pressure of pure component A and pure component B. Now, this is multiplied with XA. Instead of XA, we have substituted the second expression, and what we get is multiplied with YA PB naught divided by PA naught plus PB naught minus PA naught into YA. All we need to do is we need to take this denominator expression PA naught plus PB naught minus PA naught into YA to the left hand side and multiply it with P, that is total vapor pressure, and rearrange the whole equation and collect all the terms corresponding to this YA and obtain this total vapor pressure again. What we get in this manner is that after rearranging, we get the total vapor pressure of solution being related to vapor pressure of pure component, and more importantly is the composition in the vapor phase, that is YA. So, this is the relationship, this fourth relation, that is P equal to PA naught into PB naught divided by PA naught plus PB naught minus PA naught into YA. This fourth relationship is nothing but is the relationship which relate the total vapor pressure with the composition in vapor phase. So, these two relations, the first one relates the total vapor pressure with composition in liquid phase, the last one which relate the total vapor pressure with composition in vapor phase. But it is important to note that this first relation, if you look at it, PB naught a constant value at constant temperature, similarly PA naught minus PB naught again a constant value at constant temperature, but this XA is a variable. So, PA naught minus PB naught would serve as the slope, PB naught would serve as the intercept, and P would serve as Y. So, Y equal to mx plus this m, this x plus this c. So, therefore, this is a, if you see, the first relation is a relationship for a straight line linear equation, and this last relationship, if you explore it, that total vapor pressure is not directly proportional to amount fraction in vapor phase like that of composition in amount fraction in liquid phase, but is not directly related to composition in vapor phase, but is inverse, it has an inverse relationship between vapor pressure, total vapor pressure of solution, and composition in vapor phase, that is YA. There is inverse relationship. So, when this is an inverse relationship between the two, it means if we look at the curve between total vapor pressure and composition in vapor phase, we will obtain a parabolic curve rather than a straight line. Let us have a look at it. So, therefore, we have these four formulas overall. Let us summarize it once again. One formula which we have is which relates the total vapor pressure with that of vapor pressure of pure component A with that of vapor pressure of pure component B and amount fraction of either of the components in the liquid phase. Then we have a relationship which relates the composition in vapor phase with that of composition in liquid phase. Other relation, when we have a relationship between composition in liquid phase and composition in vapor phase. The final relation which we have is which relate the total vapor pressure of solution with that of the composition in of vapor phase, that is amount fraction of a component in its vapor phase. So, having said this, now let us apply phase rule and let us see can we draw phase diagram out of it. What phase rule implication says? According to the phase rule, we have phase rule is a general rule, as you know, that it depicts, it lets you know, or it relates the number of components, number of phases being present in the system. Since we are dealing with binary liquid mixture, so there are only two components. There are only two components means C is equal to 2. Now, therefore, phase rule equation says that F the degree of freedom equal to C minus P plus 2. When C is 2, so the phase rule equation then in that situation transform to 2 minus P plus 2, which is equal to 4 minus P. Now, it is for a binary liquid system, degree of freedom is related to 4 minus P, and it is the number of phases in that situation now which will vary and will decide the degree of freedom in that situation. If we have only a single phase, if we have suppose two liquids and we have mixed them and they are present only in liquid phase, no vapor is being formed, you can say. Why it is so, I will discuss it little later. But let us consider there is only two pure liquids which is being mixed and they go to form a solution which is homogeneous in nature. And in that situation, therefore, we have only one phase in the system, that is only liquid mixture, homogeneous liquid mixture. In that situation, the phase rule equation says F equal to 4 minus P. When we say P equal to 1, in that situation F equal to 4 minus 1 equal to 3. That is 3 degrees of freedom which are there for such a system which has only one phase, two component, that is binary liquid solution, when the solution lies only in the liquid phase, a single phase. Having said this, so it means P is equal to 1, F equal to 3. What is the meaning of degree of freedom or F? F is just nothing but is the number of variables, number of thermodynamic variables which can be varied independently without producing any change in the system. Now, let us explore what kind of thermodynamic variables we have to be specified over here for such a systems. For such a system when you have a binary liquid mixture, these variables are temperature, pressure and the composition. If there is only liquid phase in the system, so there is composition only of one phase. So therefore, temperature, pressure, composition, these are the three different thermodynamic variables to be specified. Now, since for one phase system we have obtained according to the phase rule, the degree of freedom is equal to 4 minus P, and when P, that is for one phase system only liquid phase, when you have P equal to 1, then degree of freedom equal to 3, and only three kind of variables there which is required to be specified here, that is temperature, that is pressure and composition. So what I mean to say is that you need to, in that situation, if you fix the temperature of the system, so it means you specify the temperature, you say that I will make the liquid mixture at this particular temperature, well and good. So this 1 degree of freedom is being used by you while fixing the temperature or while specifying the temperature. What else you need to do? You need to specify two more variables. These are pressure of the system, that is what is the pressure of the system to which the liquid mixture is subjected to. What is the composition, or in other words amount fraction of component A and component B in the system, or since there is only one phase, the liquid phase, so what is the amount fraction of component A and component B in the liquid phase. So these three things you are required to know. Or other way around, it could be viewed as you can vary the temperature, pressure as well as composition for such a one phase two component system binary liquid mixture without producing any change in the physical state of the system. That is another meaning of degree of freedom. Now let us explore this definition by virtue of the explore this implication on a diagram which is made between vapor pressure versus composition curve. Let us explore this vapor pressure composition curve. When we draw the curve between vapor pressure of solution with that of composition in liquid phase. Let us explore this curve. As we all know, the vapor pressure, total vapor pressure of solution is related to composition in the liquid phase and enjoys a linear relationship, that is P total equal to PA naught plus P total equal to PB naught plus PA naught minus PB naught into XA. So therefore, for such a equation we have a straight line curve, as you can see, as we have discussed earlier also, the line segment AB in that situation represent the total vapor pressure curve for such a solution. If the pressure applied on the system is greater than the total pressure at a particular composition as obtained from the Rolle's law or as is plotted at different points at different composition points on the curve AB, if the pressure exerted on the system is greater than this pressure as predicted by this straight line, Rolle's law line, in that situation you will have only one phase, that is liquid phase. And you can see it means above curve AB there is only liquid phase which would be present, because if suppose at amount fraction x a equal to 0.5, this is the point, and for this composition of solution, Rolle's law equation predict this point where the pointer is pointing out to be on the curve AB as the total vapor pressure of solution. If you exert, what I mean to say is that if you exert the vapor pressure on this solution greater than this point where the pointer is pointing out to be, then in that situation your overall state point of system will move above this curve AB. That point could be this point, this point, this point, this point, or any other point above curve AB. In that situation, what I mean to say is that there will be only stability of liquid phase in the system. And when the vapor pressure is equal to the applied pressure, in that situation what will be there? There will be vaporization. There will be equilibrium between vapors and liquid phase. So therefore, any point on the straight line AB would represent a two-phase system where liquid phase would come in equilibrium with vapor phase, and any point above curve AB would represent a system which would be only in liquid phase. So it is important to note that any point on this diagram, on this pressure versus composition curve, represent the state point of the system, or in other words overall state of the system. That overall state would be determined as liquid phase if the overall state point lies above curve AB. If the overall state point lies on curve AB, it means you will have liquid phase which will come in equilibrium with vapor phase. That is so because the total vapor pressure is an equilibrium vapor pressure. So that is equilibrium vapor pressure when there is an equilibrium between the liquid phase and the vapor phase. So therefore, on curve AB you will have liquid phase in equilibrium with vapor phase, and any point above curve AB you will have only liquid phase stable. So that is why this curve AB is called liquidus curve. And you can see this curve is being obtained when the total vapor pressure of solution is being plotted with respect to composition in liquid phase. And mind you, the composition on liquid phase on the x-axis is represented as xa equal to 1 at the right extreme side and xa equal to 0 at the left extreme position. When xa equal to 0 at left, then xb equal to 1, and when xa equal to 1 at right, then xb equal to 0. So these are complementary in nature. So it means composition in liquid phase varies between 0 and 1, that is xa varies between 0 and 1 from left to right, and xb also varies between 0 and 1 but from right to left. So this is the implication we obtain from the Rolle's law. Now let us obtain this curve. Now this is the curve which is being obtained as vapor pressure, when total vapor pressure when plotted with respect to composition in vapor phase. Now it is important to note that this is the curve having this blue curve being obtained over here. This is not the curve which is being obtained by plotting total vapor pressure versus composition in liquid phase, but is obtained when we plot total vapor pressure versus composition in vapor phase. And what is the formula for this relationship between total vapor pressure and composition in vapor phase? That is equal to, that is P, total vapor pressure, equal to product of vapor pressure of pure component A and B divided by the divide by Pb naught plus Pa naught minus Pb naught into Ya. So, that is there is a inverse relationship between total vapor pressure and composition in vapor phase, and therefore, this curve is parabolic in nature. So, you can see the two extreme points on the y axis, the vapor pressure of pure component B and pure component A, these are two extreme points. These are the same points when you had drawn the total vapor pressure versus composition in liquid phase in this curve as well, but the curve over here is parabolic in nature. Earlier curve, when you had plotted liquid phase composition, the curve was a linear line between point A and B. Now, this curve, when you plot total vapor pressure versus composition in vapor phase, this curve is parabolic in nature between again same two points A and B, where point A represent vapor pressure of pure component A and point B represent vapor pressure of pure component B. And on the coincidentally, on the x axis also, which represent now the composition in vapor phase. Here vapor phase composition also lies between 0 and 1. For example, Ya varies between 0 and 1 from left to right, and Yb varies between 0 and 1 from right to left. So, now the fact of matter is that this curve actually represent the total vapor pressure at any given composition in the vapor phase. So, it means this total vapor pressure is the equilibrium vapor pressure, and that occurs only when there is an equilibrium between liquid and vapor phase. So, it means on this curve as well there is an equilibrium, means two phases are present, but which are the two phases? Again same, vapor phase when it comes in equilibrium with liquid phase. But the very fact is that since this curve is being obtained by plotting total vapor pressure versus the composition in vapor phase, it is important to note that if we exert a pressure on the system, the exerted pressure on the system is decreased to a value lesser than that what is being predicted by the vapor pressure versus composition in vapor phase, then the system will only be in single phase, that is vapor phase. So, it means now when you plot a curve that is total vapor pressure versus composition in vapor phase, and if you subject the system to a pressure lesser than what is predicted by this curve, you will have only vapor phase being stable in the system. So, it means now in this curve, any point below this vaporous, this curve is called vaporous curve because this is the curve below which there is only vapor phase is being stable. So, now the point is that earlier curve was also plotted between composition in x axis which was lying between 0 and 1. Here this curve is being plotted between composition but in vapor phase which again lies between 0 and 1, and two extreme points on the y axis, that is pressure axis, these 2 points are being the same, vapor pressure of pure component B and vapor pressure of pure component A. So, the idea is that question arises, can we plot the two curves, that is vapor pressure versus composition in liquid phase and vapor pressure, total vapor pressure versus composition in vapor phase. Can we draw both these curves on the same plot? Answer is yes, we can. Let us have a look what kind of a curve we obtain. You see, when we draw the curve, both the curves at the same graph, we obtain this kind of a graph, where Pb naught and Pa naught, if you see it very carefully, these two extreme points are just been the same on the y axis, that is where the pressure varies. On the x axis there is composition, but it is important to note over here that on the x axis now at this point of time there are 3 variables which are being plotted. One is Ya, which varies between 0 and 1. Ya means amount fraction of component A in vapor phase, and what is small xa? Small xa is amount fraction of component A in the liquid phase, and these two phases when are in equilibrium with each other. So it means if we have a system and in the system we have liquid phase and we have vapor phase, in both the phases both components are present, A and B, then in that situation we can say in vapor phase there is Ya and Yb, and in liquid phase there is Xa and small xa and small xb. Again we should note it very carefully that since the system contains both liquid and vapor phase, there is another composition term which is the composition of overall system, that is represented by symbol capital X subscript A, that is amount fraction of component A in the overall system. So we have three composition terms, all having the variation between same limits, that is 0 and 1. The composition of overall system, that is what is the value of amount fraction of component A in the overall system. Next thing is small xa, that is what is the value of amount fraction of component A in the liquid phase. Third thing is composition in vapor phase, which is represented by symbols Ya, small ya, that is what is the composition of or amount fraction of component A in the vapor phase. So all these three variables, small xa, capital Xa, small ya, has same variation between extreme points 0 and 1. So it means we can plot them all on just one axis. What is it meaning? What it means actually, you would see it very carefully when we look at it, the phase diagram once again. You see, if we have any given composition, suppose where the pointer is pointing out to be, this point on the x-axis represent the amount fraction of component A in the overall system, and this is the point where now my pointer is pointing out to be. If this point represent the overall state of the system, it means there is only vapor phase in the system, because where the pointer is pointing out to be at this point of time is a point which lies below the vaporous curve. So therefore there is only vapor phase. When you raise the pressure, being exerted pressure on the system, so what it means is the pressure value increases, and it means the overall state point move upward to reach to this point where this pointer is pointing out to be. This point is being represented by symbol P min, that is minimum pressure. Now when you this means the minimum pressure at which two phase lies in equilibrium. Why this is so? Because this P min point lies only on the vaporous curve, and vaporous curve is the curve which represent the condition of pressure and composition at which two phases are in equilibrium, both the liquid and the vapor. And when you further raise the pressure on the system, it reaches to P max value. Now this is the maximum pressure at which the two phase can be in equilibrium at this same overall composition. If you raise the pressure further, and that pressure then would be lying above this curve Pb naught Pa naught, which is the liquidous curve. So therefore you will have only liquid phase being stable. So this you have a range between P max and P min value, that is minimum and maximum pressure, within which you will have a equilibrium between liquid and vapor phase, and below minimum pressure as been shown on any overall state point on the vaporous curve, below that pressure you will have only vapor phase stable in the system, and above P max value you will have only liquid phase being stable over there. So these implications we can draw from the phase diagram which is being obtained for the liquid system. There is lot more discussion about how the composition varies of the system in the two different phases, when the overall system changes or when pressure changes at a fixed temperature. Such discussions emerge from phase diagrams that will be done in the subsequent modules. Thank you so much.
With this note, thank you, sir. Thank you for the precious input to the lecture. And dear friends, you can definitely give your feedback to this lecture at info.cc@nic.in. We would be meeting again soon. Till then, take care. Goodbye. Thank you, sir. Thank you once again.